Okay, hello everyone. We have over 50 people already. So let us continue with our exciting program. And I'm very happy to introduce our next lecturer, Professor Martin Savage from University of Washington. So Martin received his master degree in Auckland in beautiful New Zealand, that you can see in his background. He then received his PhD from Caltech in 1990. He then was a postdoctoral fellow at Rutgers and UC San Diego, after which he became a faculty at Carnegie Mellon. And in 1996, he became a professor at the University of Washington and a senior fellow at the National Institute of Nuclear Theory. So Martin is among the pioneers in applying quantum computing to problems in basic science, including nuclear and high energy physics. And today he is going to tell us about using quantum simulations to describe the dynamics of the Standard Model. So welcome, Martin.
Thanks very much, Dima. That was a very generous, nice introduction. So let me share my screen. Can everybody see this?
Not yet.
No, you can't. So let me try once again. Let's try this.
Yes, you can see it.
Okay, so is this full screen for
yes,
everybody?
Yes, perfect. Yeah, now it's perfect.
Okay, great. So yeah, again, thank you for the introduction. I'm going to talk about quantum simulations of standard model field theories and where we are and where we want to get to. This is a new field and it's remarkably exciting. There's new results coming out all the time. And I'm certainly not going to do justice to all of the great work that's going on. Okay, so if you look at what's going on over the last 5 years, there's really two disruptive technologies that have entered the field, both nuclear particle and across the domain sciences, and they are machine learning, artificial intelligence, and quantum computing. So I'm going to be spending my time talking about quantum computing and quantum simulation today. But let me just say a couple of words about machine learning before moving on. So this is an area that promises to be revolutionary, both in experiment, data analysis, control, design, and also with regard to understanding and predicting within the standard model. While humans are very good at identifying and seeing clear correlations in data and also in numerical simulation, it becomes challenging after the biggest few. And machine learning and artificial intelligence has a remarkable capability in identifying even very small correlations that are missed by humans. And has really demonstrated itself to be an important technology for the future with regard to, for instance, emergent classical systems and emergent quantum systems. There's already exciting results both on the experimental side and also on the theoretical side. And these include, for instance, a completely different way for generating quantum field configurations for lattice QCD calculations to be used for classical computing. And there's, of course, much more. On the quantum computing side, there's been and quantum simulation side, there's been a gigantic boost in funding from the government, standing up 5 centers, NQI centers in the DOE and 6 centers in NSF. These centers have a broad mission, and part of it, and with different weights within the centers, quantum simulation. This is directed from materials, through to, again, standard model physics. So why is this in fact possible? So it was understood since the early 1980s and work by Feynman, Benioff, Mann, and others, the promise of quantum simulations. So at the heart of the matter is the fact that one can't understand or simulate a more complex quantum system in terms of a less complex system. And so, for instance, what this means is that classical computing, while it gets us very far in being able to make predictions for quantum systems, it certainly can't, it doesn't enable us to perform computations of all of the systems that we're interested in, or all of the properties of all of the systems. And so as a result, and so why quantum simulation is in fact a remarkable tool in this regard is because quantum mechanics works the same over an enormous range of length scales. All of the length scales that we tested, quantum mechanics is the same. So what that means is that if we're interested in simulating quantum systems at, say, 10 to the minus 15 meters, or quantum systems at the astrophysical scale, then we should be able to, in fact, map those systems onto quantum systems at, say, the size of a room or a laptop, or of an ion trap, for instance. And so this is the objective, and there's certainly been significant progress towards that, as you will see. It's not clear that one will be able to address all of the problems that we're interested in through quantum simulation. The hope is that one will be able to address many of the problems that we're interested in for standard model physics with quantum simulation, and so that's where that's where we're going. Despite the fact that quantum advantage has been identified for a computational problem, and I'll say more about this in a little bit, we're still searching for a quantum advantage for a scientific application. The hope is that it is just around the corner. So in 2019, it was truly a remarkable period for computing in general, where the first quantum advantage was identified. So Google used a 54 with 53 functional qubit system to perform a quantum simulation of random quantum circuits in about 3 minutes that the best classical computers takes days to do. And so there was many factors here demonstrated of more efficient computation using a quantum device than with a classical computer. And this is basically the threshold. So as I said, we're still looking for a quantum advantage for scientific applications, and one expects this to be in the near future. This, of course, was not a discovery or a progress that was performed in isolation. This was built upon decades of activity, collaborations between universities, national laboratories, and technology companies, both in techniques and technology, but also in people. It's also not limited to superconducting qubit systems. There's also comparable advances in trapped ion systems and other systems. So the problems that we're interested in roughly fall into a few categories. Around about 2016 and the 10 years leading up to 2016, the community performed studies and benchmarks for classical computing to understand the resources, particularly the exascale resources required to address the problems central in both nuclear physics and particle physics. While many of the problems that we have and are important to the science mission will be accomplished using exascale computing, there are classes of problems where even exascale computing is insufficient. And these are the problems where quantum computing is going to play an important role and will be and it has the potential to actually address these problems. So just a comment. Somebody's drawing on my screen as far as I can see. Is this just me?
Yes, I also see it.
It's not a problem for me at the moment, but it would be good if it didn't continue.
Yeah, I don't see how to disable it.
Okay, so let's just carry on. So one of the areas is, of course, real-time dynamics and particle production. So, for instance, we imagine the events at Brookhaven and heavy ion collisions, or at CERN hadron-hadron collisions, or hadron-ion collisions, and also at the future EIC. One has very high energy events involving two particles or a small number of particles in the initial state, and the energies are sufficient to produce enormous numbers of particles in the final state. At the moment, we don't have the capability to perform computations from beginning to end of such an event. Time evolution in Euclidean space, for instance, where we formulate our field theories at the moment, with lattice QCD, for instance, are just unable to perform such computations. On the other hand, quantum computers are designed for Hamiltonian evolution and real-time dynamics, and as such, processes like that then become a possibility for the future. And there's sort of active research and results being accumulated, including from the Brookhaven Stony Brook research group. So we wanted to look at lattice quantum field theories, electroweak sector, quantum chromodynamics, effective field theories, and in particular, these inelastic processes that are beyond the reach of our current classical technologies. Also, another class of processes that is beyond the reach of classical computing in many instances are finite density systems. And so while there's been enormous progress with lattice QCD and with other classical simulation techniques, a central part of the experimental program in understanding the universe and applications is understanding what happens to matter at finite baryon density and increasing baryon density as we move through dense matter, as one finds in astrophysical environments and also produces in the laboratory. So this is a diagram that is well known. I didn't create it, and captures very well what we want to be able to accomplish. And the challenge that we have is that moving up in net baryon density by introducing either a chemical potential or through explicitly including particles in a finite volume, there are sign problems that are encountered for Euclidean space calculations, which require exponentially growing classical resources, and we don't have enough resources. We won't have enough resources to get the precision that we need. And so when in contrast, for quantum simulations with Hamiltonian dynamics, there is no sign problem generically in those types of calculations. We don't know for the problems that are important to us, we don't yet know whether these sign problems, when we go to real-time evolution, will be amenable to quantum computation. The hope is that they will be, but it's still under exploration. And somewhere in between these, here we have dynamical systems. So we have small systems, for instance, neutrino nucleus inelastic processes, low energy nuclear reactions, neutrino dynamics in, say, supernova explosions. These are problems that are important, again, in the standard model. These are also problems that are require beyond polynomial computational resources for a classical computer, but should also be amenable to quantum simulation. And as with the previous classes, there's early progress in addressing such problems with quantum simulation. And then finally, systems with large Hilbert spaces, particularly quantum many-body problems, the dimensionality of the Hilbert space grows exponentially with the number of bodies. And there's been remarkable progress with high performance computing, again, to provide predictions of the low-lying spectra of even modest light and modest sized nuclei, with our field bringing in techniques, for instance, from quantum chemistry and other areas, particularly sophisticated applied mathematics, that have allowed us to make the progress that we've made. However, there's still a barrier that's going to require the exponentially growing registers of a quantum computer in order to address these. Okay, so if one reflects on where we've been and then thinks about where we're going, in the 20th century for high energy physics, it was really about chasing short distance fundamental interactions. Part of it was using the fact that the operator product expansion works, is convergent in many instances. This allows us to construct low energy effective field theories, for instance, of the electroweak sector, allowing us to actually include quantum fluctuations in a systematic and convergent way. The theories that we've constructed typically are perturbative and are constructed around tensor product states, for instance, the Parton model or heavy quark effective field theory. On the other side, of course, was the development of lattice QCD and non-perturbative numerical techniques to solve effective field theories, the effective theory of QCD on a discretized spacetime using high performance computing. And there's 50 years worth of technology development there that's going to be play an essential role in quantum simulation of these analogous systems. And so these techniques allowed us to shift modeling to higher orders in a rigorous effective field theory expansion. So this allowed us to identify the big piece with controlled uncertainties, and then modeling and uncertainties were pushed to parametrically higher orders. Now there was a similar story in nuclear physics in the 20th century, and that was about handling at least in low energy nuclear physics, was about handling the short range strong repulsion in the nucleon interaction. There was a period in time in the 70s where this looked an insurmountable problem, but this endeavor was reinvigorated by bringing in new technologies, new techniques from, in this case, particle physics and from chemistry, the renormalization group and effective field theory. The renormalization group allowed us to reliably flow the short range repulsion, to soften it, to enable the quantum many-body techniques to become more convergent. And so again, modeling gave way to effective field theory. Now looking forward and towards the 21st century, the frontier in both high energy physics and nuclear physics now and for the next period is going to be in quantum correlations and non-locality, both in understanding the theories that we have, but also in designing and accomplishing quantum simulations with quantum computers. And so just another word on that. So one imagines then that just as before in last century, 20th century, leading order is a tensor product state. 21st century, the leading order that is going to be optimal for quantum devices is going to be an entangled state. And so this presents a challenge to the theorists to be able to figure out how to identify leading order entangled states as starting points for computations. Complexity. So the complexity of the problem, if you like, the complexity class defines for a general problem, general set of parameters in your problem, the scaling of computational resources as the size of the system becomes large. It's the asymptotic behavior. And there's a very nice article from a number of years ago by Scott Aronson in Scientific American that contained this figure here on the left that mapped out the complexity classes for classical computing, but then also sketched in here the BQP. These are the class of problems that will be solved efficiently on quantum devices. And so there's been, and since that time, there's been progress in understanding the complexity classes of some generic problems for quantum devices. So here on the right, we see a rough sketch analogous to the one on the left. So there's BQP, there's BQP complete. So BQP is bounded polynomial scaling resources, polynomial scaling quantum resources, BQP complete, and then we have outside of that QMA and QMA complete. And so a couple of really important results for the standard model is interacting lattice scalar field theory is BQP complete, which means this can be simulated efficiently, including in the presence of external classical sources using a quantum computer. It also means that all of the problems that are in BQP and can be addressed efficiently on a through quantum simulation are related by polynomial resources to interacting lattice scalar field theory. So if one understands how to solve the relevant aspects of interacting lattice scalar field theory for a problem you're interested in, then you can also solve that problem. In contrast, finding the ground state of a 2-body, 3-body local Hamiltonian is outside of BQP, sits in QMA complete. So this is in a different complexity class than solving interacting lattice scalar field theory. Now the question is what does this mean for us? So should complexity be a limitation? And so our current thinking is not until it is. We've made remarkable progress in using high performance computing, classical computation to address problems that we have, even though we didn't really consider or worry about the complexity class they sat in. And so, for instance, in the near term or for the foreseeable future, the resources that we will have available to us for quantum simulation are not close to asymptotic. And it's also the case that a high order polynomial is worse when it comes to a practical simulation implementation than something with an exponential with an argument that's a small number. And so the quantum chemists have figured this out a while ago. And so when looking at the scaling of resources, one not only needs to look at whether it's exponential or polynomial, but also the arguments and the coefficients of these terms. So for example, x to the 10 is worse than e to the minus 0.01, e to the plus 0.01x until about x of 9,000. Further, the B in BQP, the B stands for bounded, which means that because of the intrinsic statistical nature of quantum simulation, when one performs a simulation, there's going to be an uncertainty or an error associated with it. And so that gives theorists then wiggle room. That is, for a given error, it might be more efficient and desirable to simulate a theory that's close to the one you want, and then perform perturbative corrections to get to where you want to go to. And effectively, this is what one does in classical simulations all the time. Lattice QCD is not continuum QCD, it's on a discretized spacetime lattice, but we know how to systematically correct for those systematic errors. So there's a very nice result early on in the study of quantum information science, Seth Lloyd, that the time evolution of an arbitrary state is within the BQP complexity class, which means it can be performed efficiently on a quantum device. And the expectation is that if one has n degrees of freedom you're trying to simulate and they're interacting for some time t, that this can be simulated efficiently with n degrees of freedom being evolved through n discrete time steps through, for instance, strata evolution. This situation is modified only slightly when dealing with fermions, where the n times t operations is replaced by polynomial in n times t, which doesn't change the asymptotic scaling, doesn't take it outside of the class. And so then one fully expects that the quantum systems of interest with n degrees of freedom, one can perform n finite time steps and recover the result that you desire within some level of precision. It's also the case and also known that d-dimensional simulations are optimally simulated with d-dimensional systems. And so, for instance, if one wishes to simulate a two-dimensional quantum system, this will be accomplished optimally with a two-dimensional quantum simulation. But this also means that if you're looking to simulate three-dimensional quantum field theories, then a two-dimensional quantum system simulation or a one-dimensional system is not going to be optimal. And you're really going to be looking to work with three-dimensional quantum simulators and quantum computers. So really, for us simulating the electroweak sector or quantum chromodynamics in 3 dimensions, we're going to be looking to accomplish that with a three-dimensional layout on a quantum device. And so this necessarily points to the need towards close collaboration between the development of simulation hardware, algorithms, and the domain scientists. But we already knew this was going to be necessary. So for quantum fields, we're going to work with a finite discretized lattice for space-time. We're going to be wanting to do this in 3 dimensions. We're going to be implementing real-time Hamiltonian evolution, and we're going to be working with, in general, for a purely universal digital quantum computer with finite Hilbert spaces, finite dimensional Hilbert spaces. And so one of the challenges that we face is to understand how we map our system onto finite dimensional Hilbert spaces. And this is, of course, something that's been under discussion since the 1980s. And of course, along with that, we have to define the boundary conditions on the fields. It's important to recognize that any such device will be embedded in a large classical computing environment. So it makes sense. And perhaps it's going to be the optimal path forward is to consider hybrid calculations where the simulation of interest, one spends significant effort in understanding how that splits into tasks that can be performed on a classical device and tasks that can be performed on the quantum device, and then distributes the tasks appropriately. Certainly that's how all of the simulations are performed today. And that's just something that will probably be the optimal path forward for the foreseeable future. When it comes to mappings of the system of interest, be it the electroweak sector or for QCD simulations, then there's no unique path forward. At the moment, there are no winners and there's no losers in this regard. And so all possible algorithms and all possible mappings and simulation techniques are to be explored. And so, for instance, for QCD, one can imagine, or scalar field theory, one can imagine having a fixed number of qubits per lattice site that are then distributed on a grid, or one can imagine having a grid with a single qubit distributed over some fabric, and then renormalization group scaling is used to recover the theory of interest. Or one can imagine having different numbers of qubits distributed on the lattice sites depending on where the support of the wave function is for particular processes. All of those are reasonable. Some are more advanced in their understanding of the scalability, as I'll mention in a little bit. Yeah, so as a result of this, then in addition to the uncertainties and errors that we understand in classical computing, there are additional errors and uncertainties that arise in quantum simulation. So these are further errors that need to be quantified and understood, and also we need to understand how they can be removed and systematically reduced to meet the precision target that we have. So the gold standard in particular for simulations of quantum field theories is for lattice scalar field theory, and it was given by Jordan Lee Preskel and Jordan Lee Crovey Preskel. And there was a nice overview of this given at a recent workshop at IQSS by Nicholas Muller. And so for this particular simulation strategy, there's a finite number of qubits are positioned at each site on the three-dimensional lattice. One initializes the non-interacting theory, which can be done because one understands the non-interacting theory. And then one creates two wave packets in this non-interacting theory. And then systematically and adiabatically evolves the system forward and backward in time to go from the non-interacting theory to the interacting theory. And then those wave packets are then released. They encounter each other, they scatter, they produce a final state, and then that final state is measured through having either detectors in your system or however else you're going to measure them. But from that, you can extract the S matrix elements in lattice scalar field theory with a controllable error. So the analysis that this group did was such that you had full control of the error at each step of the calculation. So there were a number of studies that followed to looking at the convergence. It turns out through some nice theorems from in classical information theory, Nyquist-Shannon sampling, that in fact the fact that you have a finite Hilbert space on the lattice sites is not generically a problem because it's actually doubly exponentially convergent as opposed to exponentially convergent. And so one is able to actually eliminate that error in a particular basis. And I won't talk about that. So when it comes with regard to lattice field theory, there's been significant progress in low dimensional theories and also moving to higher dimensions. The Schwinger model is particularly interesting. It's a one-dimensional quantum electrodynamics, but it shares features of QCD in 3 dimensions. In particular, charges are screened. There's a non-zero fermion condensate, and it also has non-trivial topology via a theta term. The chairman of this meeting, Diemer, is of course one of the experts in here and has been performing simulations of this theory. In 2016, the first quantum simulation was released. It came out of the Innsbruck group, and it showed just a very simple 2 spatial site lattice with 4 qubits of E plus E minus pairs emerging from the trivial vacuum through time evolution. This is a problem that, of course, can be solved on a classical computer, but it points the way towards simulations that go beyond classical computing, and that was the real value of this calculation. It's also the case that in the Schwinger model, there are 2-body bound states and 3-body bound states, which means that at least one can go some small step towards looking towards potentially simulations that mirror something we'd find in nuclear physics for the deuteron triton. The lattice discretization is quite simple. It has the form here sitting on the lower left. Just a hopping term, the energy in the electric field, and then also a mass term. There's been a number of results obtained on trapped ion systems. This was the one I mentioned to you. This is what started the field. Work on superconducting qubit systems that I was involved in. More work from Innsbruck on a larger device looking at VQE algorithms to identify the ground state. There was work from the University of Maryland group in understanding how to do much better in the time evolution that had been done before. So this is a classical simulation of their algorithm and their method, which shows great advances. There was work by Diemer and collaborators Kikuchi looking at the impact of a quench on the real-time dynamics of the system, which is something that, this was the first time this was explored. It was very interesting. So what's shown here is the vector current as a function of time with a quench in theta. And there's also work by Chakrabarty, Honda, Tsubuchi, and Tomania with Brookhaven and Oxford, looking at identifying the ground state of the Schwinger model in the presence of a non-zero value of theta. And for classical simulation, this introduces a sign problem, but as I mentioned before, for quantum simulation, it doesn't, and they were able to efficiently identify and solve on a simulator. There's also a paper came out in the last 2 years on looking at quantifying resources required in going to scale for simulations of the lattice Schwinger model. by Shaw, Lugowski, Stryker, and Wiebe. And so this is moving along the path and moved along the path in the same way as the Jordan Lee Priskel work for scalar field theory. Now, there's been some amazing advances in technology and simulations of technology. And I'm certainly not going to be able to do justice to them all during this talk. One of the ones that came out of left field for me was quantum circuits, and the fact that you can set up circuits of Josephson junctions and capacitors to perform analog simulations of scalar field theory, where the scalar field's identified as the superconducting phase. And so this group, Ananda Roy and collaborators, looked at both these quantum circuit simulations of scalar conformal field theories and also of the lattice Sine-Gordon model. They performed a number of classical simulations to show that, in fact, one can do interesting physics with such devices. And so both of these are very interesting. This, of course, maps well to the work with the Schwinger model. This one's interesting for different reasons, because it allows you, gives you the capability to start looking at entanglement and multi-body entanglement in a massless scalar theory that's proved interesting in other arenas. There's been recent progress in also using and simulating Rydberg atom arrays for link models and gauge theories. And this is a compilation of slides I took from a talk given by Federica Sirachi at the same IQSS meeting as before. So the Rydberg atoms, of course, were suggested as being a way for simulating a number of systems, including lattice gauge theories, more than 10 years ago now, by Peter Zoller and collaborators. And here's a picture of experimental results from control of such atoms. So there's universality in these simulators in the sense that the Rydberg atom tends towards being a universal system. And so the community and these people and a significant community beyond have understood and made progress in how one can look at low dimensional systems, in particular, for instance, an SUN cross U1 using a quantum link model, which constitutes a truncation of the gauge field, and which I won't dwell on. But the algorithm and how one uses the Rydberg arrays to perform simulations is now understood, and progress is being made to do such simulations. The extension to 2 dimensions is more challenging, but there's again good progress being made here. For instance, in this upper left, an algorithm for U1 lattice gauge theory in 2+1 dimensions. It requires different controls on the Rydberg atoms and the interactions. It requires, in fact, p states, but it seems that this can actually be done. And then there's simulations of what one expects for an n=2 system. So this would be 4 matter sites and H gauge sites using periodic boundary conditions. And one sees the results of the simulations here, including tests of violations of Gauss's law. There's a suggestion for hybrid analog digital simulations using trapped ion technologies. This is recent work this year out of the Maryland group, Davudi, Linke, and Pagano, where they suggested and simulated using introducing interactions and modifying the local phonon modes and using those modes as bosonic degrees of freedom in the simulation. So that's really exciting. They mapped out a gate set, including the old gate set and some new gate sets, particularly this new local spin phonon gate, and then figured out and wrote down the quantum circuits one would need to actually perform simulations of Yukawa theory and the Schwinger model and another theory that I forget. So this looks very exciting. The bosons have presented a challenge. So this is a different and creative approach for actually handling them within a quantum simulation. That same group also made progress in understanding how one could implement a three-body force with trapped ion simulations. And so in the same way as one derives the Malmer-Sorensen gate from an expansion plane wave, one can also perform an expansion and then try and compensate for additional terms to actually isolate a three-body interaction from the applications of the appropriate lasers. And so they've successfully figured out and demonstrated how to do that. So for QCD, and I'm running out of time. So for QCD, let me just outline the ideas that people have going forward. So think about Yang Mills, no fermions, and so then one has chromoelectric fields and chromomagnetic fields moving between each of the lattice sites, and one has gauge invariant issue 3 spaces on each of the vertices of this lattice. There was a paper explaining how one could go about simulating these theories by Burns and Yamamoto back in 2006, and so all subsequent works have really built on that. And that paper was built on the Kogut-Susskind Hamiltonian that was written down in the early 1970s. So the Hamiltonian has the form of a contribution from the electric chromoelectric fields and a contribution from the chromomagnetic fields in the basis where the electric flux operator is diagonal, then the chromomagnetic interactions transition between the different eigenstates of the E² operator. And so one of the mappings that you can do, and an efficient one, is to have qubits on each associated with each of these links, and one can have multiple registers of qubits. Turns out to be efficient after integrating over the gauge spaces to have just 2, one associated with the number of up indices on an SUN tensor and one with the number of down indices on an SUN tensor. And then the wave function of the system is a coherent superposition of these configurations on each of the links between lattice sites. So there's some big wave function in general that sits in your quantum register. So this is a local construction. It scales well. There's some classical processing that has to happen, of course, because one's dealing with an SUN group and one has to figure out transition amplitudes and so forth. It was shown by Bacon, Chung, and Harrow in 2006 that, in fact, creating these SUN Clebsch-Gordon coefficients reside in BQP. So this is something that one can also do efficiently on a quantum computer. Gauss's law, as with all of the other field theories that we've talked about, also must be enforced by hand. And so one has to check, and of course, if there's an error, if there's a bit flip or something on one of these links, then of course Gauss's law will be violated. And I'll say a little bit more about that in a bit. So we performed the first calculation of an SU3 gauge theory on a quantum device. It was very simple. It was 1 plaquette. So this is effectively t = -1. But nonetheless, it provided a way for us to explore the behavior of convergence with regard to truncations of the color representations, and also look at some of the pathologies one might encounter. In these low dimensional theories, the wave functions are localized for a given lattice spacing, even though that word doesn't really apply to a single plaquette. And we were able to establish some benchmarks with IBM's superconducting qubit systems, the Athens chip. And so we're looking for others to benchmark this system on different devices to see how they compare. And I should say this was done with my student Anthony Ciavarella and Natalie Clark. So as part of the simulation, there was controls that had to be identified, particularly the amplitude for transitioning these links between some IRAP and another IRAP depended on the chromo flux actually entering into this vertex. And this, of course, when we have this embedded in 3 dimensions or n dimensions, then of course one can always perform combinations to figure out what the net flux into this vertex is. If you look at the scaling of the classical processing that was required to do that, then if you just consider the 1 and the 3 and the 8, for instance, then in the 3-bar, then you have about 1,000 matrix elements to compute. But by the time you've gone up to including the 24-dimensional array, then you have 24 million. So the classical computing resources scale, in this case, roughly like the truncation cutoff to the 12th power. And then more generally, it's to the 2 to the n number of different links coming into the vertex times some power. So one sees that this is a large, growing but polynomial classical resource required for in order to implement the quantum simulation. There's work coming out of Toronto, and Randy Lewis and collaborators, and Christine Mushek, that looked at issue 2 in 1 dimension. And they were able to use VQE to establish the energy of the ground state, but also of the first hadronic excitation in the state, the meson. And so they were able to actually solve this 1-dimensional non-abelian gauge theory and find the first hadron. So this was a really nice step forward. Like in 1 dimension with the Schwinger model, the gauge fields are non-dynamical and can be integrated out explicitly, and one expects this to also happen for larger SUN. Okay, so I need to stop in a couple of minutes, so let me just say a couple more words. So there's been significant progress in looking at simulations of spin models. So these spin models are remarkably valuable in giving us insight and understanding how we're going to do simulations of more complex systems like lattice gauge theories. And so I show the results here from Ash Milstead and collaborators. So they used a one-dimensional system. This system supports a kink, and for the Ising coupling, where lambda is 0, then these kinks move towards each other and they scatter off each other repeatedly. And one sees an evolution of the entanglement entropy as a function of time as they scatter from each other, but one doesn't see any inelasticities. There's no particles that go off to infinity away from the center of mass of these domain walls. On the other hand, when you turn on this coupling lambda, then one sees, in fact, in addition to these walls, these topological objects interacting with each other and the entanglement entropy varying as a function of time, one also sees the inelastic production of ballistic particles that go off to infinity. So when we're studying QCD, we're going to be in this situation with ballistic particles when we're above certain thresholds. And so studying what happens in these simpler models is really beneficial and revealing. Okay, so I'm going to jump a few things. Well, actually, let me go back. So beyond lattice gauge theories, of course, there's numbers of other quantum simulations, as I mentioned earlier. So one of the ones that's also interesting is the study of neutrino oscillations in astrophysical environments where neutrinos get to interact with themselves. The density of neutrinos is high enough that they interact with themselves. They couple to the lepton number. And so as a result, one can map this problem for coherent forward scattering onto spin models, the single spin and then the double spin. And depending on what the initial configuration is, then one seeing interesting overlap with the phenomena that are studied in condensed matter physics, dynamical phase transitions. So these studies are just beginning, but again, they're being enabled by advances in classical algorithms, but also for quantum simulation. Okay, I'm really going to have to jump a number of things here. Let me. So when it comes to error correction, we're in the NISQ era, noisy intermediate scale quantum, and just a couple of years ago, we didn't think that error correction was going to be anything practical for us to think about anytime soon, but that's changed. There's been a number of results now from devices One of them was Google's demonstration of exponential convergence for using the repetition code for single qubit flips, and the suppression and the creation, the use of increasing number of qubits, exponential suppression and fidelity of a logical qubit, as shown here. So that was from earlier this year. And then also a result from Honeywell on establishing the building blocks for implementations of a simple, of a color code equivalent to the 713 Steen code. So it looks like we should really be thinking now about using logical qubits and error correction as something that may be practical in the near future. And that's different from a couple of years ago. Okay, so let me close. I'm over time. So we're in this remarkable period for quantum simulation. There are many developments, both hardware, algorithmic, and we're really just starting to get our heads around how we're going to begin to simulate basic aspects of quantum field theory on the road to performing simulations that we need to support the experimental program and to make progress in understanding the standard model. Non-equilibrium dynamics, inelastic processes, the structure of large nuclei, and neutrinos in dense systems, just to name a few. It's very clear that co-design and development and cooperation between all of these advancing areas is important. And the frontier is quantum correlations and entanglement, both understanding it in our systems and using it for quantum simulations. Thanks very much.
Thank you very much, Martin, for this beautiful lecture. So I'm sure there will be many questions, and just as in the morning, you can ask your question by either raising hand through reactions tab, or you can type your questions in the chat, as you prefer. Okay, maybe as people are thinking about questions, let me ask the first question. So what is your current estimate for the number of qubits that we would need to simulate real QCD in 3+1 dimensions for SU3?
Yeah, so it's much less than it was a couple of years ago. I don't have a firm number on the top of my head, but there's a couple of things that have made this estimate become much less than I thought it was. So firstly, it was recognized by Banyuls and Carl Janssen and others, and also by ourselves, that you can, at least for Yang-Mills and generically the full QCD, you can integrate over the gauge space at each of the vertices. So you don't need to support all of the quantum numbers in the spaces, and you can just then support the quantum numbers, the dimensionality of the IREP on the link. And so that saves a lot. It comes at a price that I showed you of those polynomial scaling classical resources to generate the matrix elements. And the other thing is that at least in low dimensions, the wave functions in these color spaces for the ground state and low-lying states is exponentially, it's Gaussian localized in the low dimensional IREPs. That of course spreads as you reduce the lattice spacing and the magnetic terms become more and more important. But at least for some finite lattice spacing, and I don't know what it is, I don't know what corresponds to 0.1, 0.1 Fermi or 0.05 or, but at least, there is a regime where in fact you can live and you have a localized wave function. How that works in 3 dimensions, don't know yet. That's something that we have to figure out, of course, that with the logarithmic, the renormal, they're super renormalizable, as you know, in 1 and 2 and not 3. And so I don't understand what happens in 3 dimensions. But I think the qubit count is much less than it was before. But I really don't know the number now. I think that's certainly one of the things to really determine now, is to quantify that. But yeah, that's a really good question.
Thank you. So we have a question from Jose Guerra. The question is, do you think applied machine learning can be utilized to simplify the calculations and gain novel insight?
So I think the answer is yes. I can't give you an example of, a rigorous example of where that is the case. One of the challenges that we are just grappling with is to figure out how to initialize and what does the ground state look like? How would you initialize your quantum device? And there's, as I mentioned on my second slide, there's machine learning is about finding correlations. Part of it's about finding correlations that we don't see by eye and we can't find, beyond the lowest 2, 3, 4-point functions. So I think machine learning will play an important role there in understanding how to initialize the states that we want. And that's just the beginning. To understand how to compress the circuits and do the evolution as we go to scale, all of these things is going to require machine learning.
Mm-hmm. Okay, so then there are two questions from Bilal. So question one, entanglement is the key of quantum computing. How it depends on entangled particle. Let's see, I'm not quite sure what is meant by this. Maybe how it scales with the number of entangled particles.
So I don't see this question.
It's in the chat by Bilal.
Yeah, I'm not seeing it in the chat.
Oh, I see. It was sent to me as a direct message. So that's
right.
So let me maybe also read her second question. Why quantum computing of Google, IBM, Honeywell, Canada are different? Can we make one universal quantum computing which would be similar at every quantum computer?
Sorry, can you say that again? I missed the question. Here.
Okay, so the question is that quantum computers built by Google, IBM, Honeywell, and so on are all different. Right. Can we make one universal quantum computer?
Yeah, so that's a good question, and the answer is you can. As long as you have the capabilities, you can make the quantum computer any way you like, as long as it can execute a universal gate set. And there is no clear preference at this point as to what's going to go to scale. So all of these devices are interesting and pushing the frontiers. They have different properties. So the superconducting systems, they have you can apply gates in very short timescales. The trapped ion systems, the gate time is longer, but the qubits are of higher fidelity. And so these quantum systems have just different properties. And at the moment, different problems are better suited for the different architectures, but one hopes that asymptotically in the future, when one gets to sort of commodity quantum devices like a laptop, then you won't be able to tell the difference, what's under your keyboard, whether it's running a trapped ion system or a superconducting system. It should be invisible to the user, but we are so far from that at the moment.
Mm-hmm. So next question, Zach. So he has his hand raised.
Yes, I first tried to clap and it didn't work. So Martin, I want to ask, at the beginning you mentioned that Google had achieved quantum advantage. So the first question is, why could that happen? What and more generally, what is the class of problems for that is possible? And in particular, what kind of problems we are thinking of? For what kind of problems would that be possible?
Yeah, so the problem was looking at random quantum circuits and looking at the distributions of outcomes. And by construction, it's something that is intrinsically quantum and asymptotically beyond the capabilities of a classical computer. And so in some ways it was the best case scenario and contrived to find a quantum advantage. And it succeeded. Now, the problems that we have for scientific applications, we're still in the process of trying to understand what that is. And at the moment, the circuit designs that we're all doing are pretty small and modest size because the available volumes are small. But we haven't really figured out the parts that are best suited to the quantum device and the parts that are best suited for classical devices. So this is still something that has to be done. So we're not.
For example, random number generation.
Sorry, the what? Sorry.
Random number generation, could that be done faster on a quantum computer than a classical one?
A random number generation, yes.
Yeah.
Yes.
Okay, excellent. So
Okay,
then the next question is from Shamim. So Shamim is a EEE student. And the question is, how can I go from being a student to theoretical physics simulation with quantum computing? Is the bridge gap big? How big is the bridge gap?
At the moment, I would suggest there's no gap at all. We're still at the beginning, or even some ways before the beginning, and so we're all learning. And from the scientific application side of things, there's so much information that's been developed in engineering and quantum information science, condensed matter, and other areas that we're trying to learn and understand and integrate. We have a lot of specialized knowledge on the standard model side that we're bringing to bear on the problem, but it's going to be a coherent effort. And so at this point, there is no barrier really in entering this field.
Excellent. Next question is from Alan Rahanimov. And the question is, do you think the future of qubit manufacturing lies in production of quantum dots and similar zero-dimensional nanomaterials? And do you see the cost of production falling in the near future for quantum computing devices?
Yeah, so I'm probably the last person to ask this question to, because I just don't know the answer to this. I mean, there's recent progress that was announced by Intel and silicon, quantum dots in silicon, and that's certainly something that can go to scale, given we've seen what's happened with classical computing in silicon. But I really don't know at the moment what the future looks like. It's certainly the case.
What's the back?
It's certainly the case that one expects to be able to. One expects that there'll be at least one technology that can go to scale efficiently and go to commodity. But I'm just not the person to give you an answer for this. You should ask somebody that knows this for real.